To understand the foundation of the oscillatory dynamics transductive bridging theorem, or ODTBT, we start with its central variable, recursive phase strain, denoted as delta phi. In the existing mathematical structure, this behaves strictly as a classical dynamic coordinate. It moves. It has a kinetic term, much like a physical object in motion. This kinetic structure allows us to define a classical conjugate momentum density for the system. This equation breaks down into two distinct parts derived from the L1 Lagrangian layer. First, we have the strain inertia coefficient, alpha effective, multiplied by the phase velocity. Then we add chi, which accounts for velocity-dependent coupling. Notice what is missing from this equation. Planck's constant, h bar, the defining signature of quantum mechanics, is entirely absent from the bedrock formulation. The corpus provides a complete classical Hamiltonian mechanics, but nothing more. The logical next step for this research program is to push these strictly classical dynamics into a quantized framework, allowing delta phi to be treated as a canonical phase coordinate. Moving from a classical Hamiltonian to a quantum framework requires building a deliberate mathematical bridge. We cannot assume a quantum structure exists hidden inside the background equations. We have to construct it. In theoretical physics, there is a persistent danger of self-deception. It is tempting to look at a classical scalar field and claim to discover quantum mechanics already buried within it, extracting parameters that were never actually there. To prevent this, ODTBT enforces a formal honesty claim. This rule mandates that we explicitly separate the mechanics already derived within the theory's corpus from any new mathematical extensions we construct to overlay on top of it. We start by mapping our established variables. The L1 Lagrangian, the kinetic term, and the strain inertia coefficient all belong strictly on the left side, the corpus substrate. The right side remains a completely empty void. The architectural rule here is rigid. No variable, coefficient, or structural assumption is allowed to cross this central boundary silently. Every addition must be declared. Maintaining this labeled boundary prevents mathematical cheating. By isolating what the theory provides versus what the researcher supplies, the structural integrity of the physics remains intact. The challenge begins when we attempt to quantize delta phi. In the existing corpus, delta phi appears inside sign functions, specifically within the coherent scalar. This yields a periodic readout, meaning the output repeats at regular intervals. A periodic readout is mathematically distinct from a variable being intrinsically compact. A clock face reads time in a repeating 12-hour cycle, but time itself stretches linearly. We do not know if delta phi is an infinitely stretching real number or a strictly bounded angle. If we force delta phi into the role of a standard phase operator, we hit the Susskind-Glogower obstruction. This established proof shows that naive phase operators fail when they are conjugate to a number operator with a bounded below spectrum. The geometry fails to close. To bypass this topological dead end, we construct a safer alternative, the exponentiated unitary operator, U delta, defined as e to the power of I times delta phi. Notice its position on our map. It is placed entirely on the right side, the extension layer. Exponentiating the phase is a manufactured solution. We choose to treat delta phi as if it were compact to avoid known topological traps.
We are engineering a way forward rather than extracting a feature from the classical text. With the phase operator defined, we must build the other half of our canonical pair, the conjugate momentum. We define a newly constructed action-like variable, j delta. To make this function, we introduce a critical scaling parameter, alpha delta. Compare this directly with our earlier classical variable. Alpha effective is the strain inertia derived from the baseline equations. Alpha delta is a distinct action scale normalizer. Alpha delta is alien to the existing corpus. It cannot be derived from the L1 Lagrangian or the field equations. It is a parameter supplied by the researcher to enforce canonical commutation. This specific supplied parameter acts as the mathematical gateway where we manually inject the quantum of action. It is through alpha delta that Planck's constant, h bar, finally enters the system. By deliberately adding alpha delta, we explicitly introduce quantization from the outside.
This finalizes the proof that the canonical phase structure of ODTBT is an extension actively being built, not an inherent property being uncovered. We now have our fully assembled canonical pair, the action variable J delta and the exponentiated phase operator U delta. They are ready for commutation. We define the target relation as the √2 exponentiated commutator. The commutator of J delta and U delta equals H bar times U delta. Breaking it apart reveals its internal scaffolding, swapping in our manufactured exponent and our normalizer. We use this exact formulation because the naive position momentum commutator, known as √1, only functions as a local semi-classical approximation. It fails as a global solution for periodic variables. √2 avoids these domain contradictions. Let's conduct a final boundary audit. The unitary phase U delta, the normalizer alpha delta, the action variable J delta, and Planck's constant all reside strictly on the extension side of the architectural map. The √2 structure creates a mathematically safe, globally valid environment for quantization. We have built a functional quantum overlay without corrupting the classical bedrock equations that support it. While this mathematical scaffolding is strict, the work is incomplete. Several load-bearing connections remain unbuilt, existing right now as open pathways. First, the current action variable is a leading order approximation. It requires a fully coupled treatment that actively incorporates the classical velocity coupling, chi, into the new momentum density construction. Second, we supplied alpha delta to normalize the action, but we have yet to determine its physical reality. The exact mechanism that fixes the magnitude of this parameter in nature is an open question. Third, we must theoretically prove whether the recursive field update operator, known as Fpsi, actively generates these specific phase shifts across the system. By defining the limits of the current extension, we map out precisely what comes next. Identifying these specific mathematical gaps transforms them into highly focused targets for future derivation. To advance the physics, we expanded the theory by building rigorous scaffolding and explicitly supplying parameters like Planck's constant from the outside. At no point did we discover a hidden quantum layer buried natively inside the classical scalar equations. We constructed a canonical phase framework because the existing math permitted it, not because it provided it. Transparency in separating derivation from construction keeps the formalism honest as it grows.